Hi, everyone. My name is Praful. I work with this company called Cozier. It's an honor to be here today, at least virtually. I apologize I couldn't make it in person to the conference due to some traveling conflicts. What we are going to talk about is a new algorithm for AI called Calibrated Quantum Mesh. We have successfully used this for natural language understanding, particularly natural language search. And today we want to just talk about the motivation of this algorithm and the results that it's been showing. So as you know, deep learning is the prevalent algorithm people have been using in AI, and it comes in many varieties. The problem is that when you use it for structured data set, it works pretty well. But when you drag it to unstructured data set, the accuracy does not cross a 75 to 80% threshold, which is great, but businesses do not work on that accuracy. If you have to automate a workflow, the businesses demand 95% plus accuracy. So we have worked with deep learning and calibrated quantum mesh for about 6 years now. And the original motivation for CQM was that for the unstructured data sets, we were unable to train deep learning beyond a certain accuracy. And even for that, training a deep learning algo takes lots and lots of data. Now, again, if you're talking about structured data sets like click streams or viewership records or just kind of user behavior on a website, you have those billions of records that can be used for deep learning. Big companies like Google, Facebook, Apple, they also have lots of data and resources to manage the data to train a deep neural network model. But in most situations, in most real enterprise situations, that kind of data does not exist. And so apart from the accuracy, there was another demand from the business, which is, can something train on either publicly available data or the limited data that enterprises really have? Similarly, even if they have the data, they do not have enough resources to annotate the data. And again, that's the problem with deep learning. It's an algorithm written for structured data sets. So if you use unstructured data sets, they need to be trained, or I'm sorry, they need to be annotated before deep learning can learn anything. So, and again, the poster child of this problem has been the debacle of Watson with MD Anderson, where they spent about $60 million and 3 years training an oncology data set, but it didn't get them anything because of obvious reasons. So that was the motivation of writing a new algo altogether, which is meant for unstructured data sets. In this talk, I will just touch on the basics of it. We are going to publish more and more in the coming years, which kind of cover the essence of this algorithm. And please stay tuned with our publications to learn more. But the basic is this. In natural language, when humans communicate, the same word, the same keywords, the same phrase could mean so many different things. Conversely, the same idea can be expressed into permutations of so many different keywords. So the first thing we do is that we never model key to a value. We never model that this keyword means this particular thing, or this variable has this particular value. We always model a variable to a probability distribution. And also and as you'll continue, you'll see that this probability distribution is very kind of quantumized. It's not a continuum. And so we call them quantum states, and each variable can have multiple quantum states, which is the first kind of basic principle of a design of a calibrated quantum mesh, which you can also do. It's pretty trivial to program. The next thing we realize about human cognitive behavior is that everything is interconnected. So if you take a language like English, there's about 100,000 tokens which cover about 95 to 98% of the language, while there's the entire language can be written down in just 170,000 words. But the meanings, there's almost infinite amount of meaning that can be expressed through those tokens and words, and that comes together as a combination of the tokens and the way the tokens are connected and the way the tokens are written. So if you can take these 200,000 tokens, let's just say, so at the bottom, and then you start connecting them in the way they are used together to form meaningful or to meaningful things or to express ideas, then you start building up almost a three-dimensional mesh. It's very much like the concept is derived from a probabilistic graphical models or networks, the difference really is that each of these edges define a constraint or an association, and the value or the strength of that association is essentially learned based on the corpus or the usage in the traditional way an AI model learns. So which is the third step of a calibrated quantum mesh algorithm, which is that you have this mesh which is interconnected, it's constrained, but then you take the external evidence, which is from the corpus you're ingesting, and or the usage of the data or any other external evidence you can provide, and essentially you come up with a refined probabilistic distribution. Now, from engineering point of view, we kind of assume things like beyond 2 sigma. So if it's 95% likely, then we assume it's 100% likely, and things like that. In some cases it works well, in some cases it doesn't. But those are kind of really modeling and engineering problems. But as an overall concept, if you can take a variable and map it across its all possible quantum states, then you interconnect it to constraining mesh or a constraining graph where a lot of those quantum states eventually come out to with zero probability or less than trivial or near trivial probabilities. And then you can take external evidence and put more and more constraint on that particular mesh. Then you get something that is very highly qualified and very representative of the human ideas that were conveyed within that corpus, without being worried about keywords and exactly how they were expressed and what's the permutation and arrangement and stuff. So I know it's a very high level, but that's the essence of a calibrated quantum mesh, which we have developed and successfully used for natural language search. Because if you think about it, if you can translate a set of words to an idea, some kind of an abstract modeling of an idea, then what you can do is you can take a corpus and convert them into this cognitive model, which is essentially this mesh, and which contains all the ideas contained in the corpus. And the translation can also be applied to the queries, right? So the model will translate the corpus into a set of ideas, as well as the query to a set of ideas, and then it's just a matter of sorting by best match. Wherever these ideas kind of overlap, you get the right answers that way. So now what you've done by this natural language search, using CQM for natural language search, is that first of all, you have become completely independent of keywords. The same idea can be expressed or queried in different form. As long as the mesh is properly trained for that, it will still work. The second, you have given away the structure, which is a very artificial structure, an artificial structure of a document. There's all we always call it the metadata and other such things. Those are basically engineering constraint. But in terms of just a knowledge management query, everything is now contained as ideas at some level in this mesh, and you're just querying that mesh of ideas and their interconnections, and so you don't worry about the knowledge. And third, it really looks like an interaction between two humans, because you can ask human questions and get human answers, and don't worry about the document or the data structure it's contained in. It could be a document, it could be an image, it could be a table, it could be a database, and you still get the answer because that's what you were after. To demonstrate the effectiveness, now we are already working with multiple Fortune 500 enterprises, and we are really getting 95% plus accuracy, and mainly because we are able to train the mesh in a very effective way. We can translate their inherent data structures into the cognitive learnings of this mesh. But for this conference, we essentially decided to take some public corpus And the details, I won't spend too much time on that, kind of talking about this, but details are in the paper if you look it up. We essentially took up the CFPB, the Consumer Financial Protection Bureau's search functionality, which is powered by Bing, the Microsoft search engine, and and they have an open data set which is being searched. So we took that thing. We had 150 most frequently asked questions in the financial forums across the internet, queried through our engine and the Bing, and we basically did not train. We did not have the resources to train it properly. It's completely untrained data. And what we got was some of the things that you would see in the paper, where the you look at this question, Bing doesn't even answer that question, while we find the exact knowledge which essentially addresses the concern of the user, because finds the intent and goes in and matches those things. And similarly, you can see the other questions. Again, more things are there in papers. One very important aspect of a natural language search is the ability to say, I don't know. So instead of trying to, in the best effort way to give you any answer possible, if there's no match between the idea of the question you ask and the ideas contained in a corpus, the natural language search comes back and says, I don't know. Now, keep in mind that they have improved their algos since, and we have improved their algos since. So this is as of about, I think, 3 or 4 months ago. And still, we are beating them hands down. In fact, in much better numbers than what you see on this screen. In any case, we are, as I said, we are using it against real world search engines and real world enterprises, and getting a lot of traction with it. Please feel free to send any questions you have my way, and I'm happy to set up a call or just answer over email. I'm sorry I could not be there in person myself, and also keep following us for more and more details on CQM. Thank you so much.